All right, we're gonna start now. Okay, welcome back, everyone. Welcome back to 2021. Hopefully, y'all had a really good winter break and really good Christmas and New Year. Today, we're gonna go back to some lessons, and what we learned today, we're gonna learn about triangle geometry. So let's get to the topic. All right. So before we move on, here's some prerequisite terms and symbols that you need to know before we get on to the next few slides. So first thing you need to know, polygon. Polygon is just an enclosed shape with a finite number. So finite just means countable. You can count how many numbers there are. With a finite number of straight sides or edges. So sides and or edges, they both mean the same thing. Usually we would use the word edges instead of sides. So yeah, and the sides have to be straight. They can't be curved, otherwise it's not a polygon. A circle is a polygon, but it's considered like infinite straight sides. If you're curious, infinite edges. It's not just like one curved edge. It's infinite like straight edges. They're like combined together, so it looks curved. We're not going to talk about circles in today's lesson. Probably do it in like a later lesson. Oops, that means skip. Here's our second term, a vertex. Vertex is just the intersection point of two edges or two sides. Just that point. Now the third term, congruent. Congruent is just another term that means equal. So for example, I can say that two sides are congruent, or two shapes, like two triangles, that are congruent. So like they're equal in the shape and size. That's what that means. Usually we don't use the term equal when referring to like geometric problems. We usually use the word congruent instead of equal for geometry. Right? Now last two are some symbols. So this symbol right here, so it's like two edges connect together, is just to represent an angle. And the way you interpret this, say you have angle ABC. So I'm just going to refer to the symbol as angle. So angle ABC, it's the angle at vertex B, so the point B, and that's between vertices A and C. And I can show you guys an example of that. So say you have two lines, or say you have a triangle, ABC. And so angle ABC. Oh, did I stop sharing? I'm sorry about that. Okay. I know I keep clicking it. Okay, well, I'm on a canvas right now. That's what I'm doing. Sorry, guys. Here you go. Okay. So right here, I drew a triangle ABC. I named these vertices. This one A, this one B, this one C. And so if I'm referring to angle ABC, it's this angle right here. So this one. So it's referring to one on vertex B, but also between A and C. And the reason why I can't just name this angle B is because I could also be referring to this exterior angle right here. So this could be angle B, or that could also be angle B. So if I stay like that, I wouldn't know which one it would be. So that's why I have to put the A's and C's with the angle name as well. Let's go back to the slideshow. Oh, I think it's glitched out. I'm pressing share this tab, but then it just doesn't work. Okay, I'm gonna do this. Yeah, I just shared whole screen. Yeah, that'll work. So this way I can switch in between. Okay, perfect. Sorry about that. Technical issues. All right, so that's an angle. And then we just have this triangle symbol just to represent a triangle. So I can like put this triangle symbol in front of ABC, like this one. So just triangle ABC. That's how I would name this triangle, where the letters are your vertices. Any questions about these terms? No questions? I'll move on. Right. So this should be like a bit of review for triangles. So as you know, all know, a triangle is a three-sided polygon, and the interior angles, so the angles inside and in between, like the vertices, they add up to 180 degrees. That should review. And there's three types of triangles. So one type is an equilateral triangle. So if you look at the diagram, this middle one right here, we have all sides and angles are congruent or equal to each other. So if you look at all the angles, they're all 60 degrees. Right? You just do 180 divided by 3, and that'll give you all of the angles for the equilateral triangle. And then the side lengths also have to be equal. And they can vary, not unlike the angles. The angles have to say 60 degrees. Now we have a second type of triangle. We have an isosceles triangle. An isosceles triangle is where you have exactly two sides and exactly two angles that are congruent. So if you look at this triangle right here, you have these two sides that are congruent. Oh yeah, and congruent sides, they're usually measured by tick marks. So if you have two ticks on one side and then two ticks on the other side, or you also have one tick on one side and one tick on the other, doesn't matter. But this just represents that they're equal in length. And the angles, you have two angles that are also the same. So here you have 68 degrees, here you also have a 68 degrees. And notice where they're placed inside a triangle. They're so one of these angles is between one of the congruent sides, and then the third side, which is not congruent to any of these. And same thing for the second angle. It's between one congruent side and one non-congruent side. And the angle that's between the two congruent sides, that angle is different from these two. So that's a good thing to note for isosceles triangles, right? And lastly, we have scalene triangles. So where no sides or angles are congruent. So you can see here. So this one has one tick mark, this one has two tick marks, this one has three tick marks. That means that they represent the different lengths. And you also see the angles are different. So here is 63, so you have 61. This angle should be different as well if you do the math. And then the area of a triangle is just base times height. So say you have this isosceles triangle, you have the base right here, and then you multiply it by a height. Remember, the height has to be perpendicular to the base. So the height would be like around here. And then you just divide that by 2. That will give you your area. Any questions? So this is just a review of what a triangle is. No questions? Then move on. All right. And this also might be reviewed to you guys, but the Pythagorean theorem. This is really important for triangle geometry. So Pythagorean theorem, this only applies to right triangles. So right triangles are just triangles with a 90-degree angle. Just one. You can have two 90-degree angles, or else that would add up to 180 immediately, and then you can have a third angle. Right? And so this Pythagorean theorem, it's used to determine an unknown side length of right triangles if you're given two of the side lengths. So, and the formula looks like this. So it's a squared plus b squared equal to c squared. And what do these variables represent? So we have a and b. They're called the legs of the right triangle. So legs are the two shortest sides. So I can see in the diagram here, this is a, this is b. You can also switch them in between, but these are the two shortest sides of the triangle. Oops. And then c is called the hypotenuse. So c has to be on the opposite side for the equation. On the equation, c squared has to be on the opposite side of the two legs. So the hypotenuse is just the longest side of the triangle. So you can see over here, this is the longest side, and they call it c as well. And here's another term to know: Pythagorean triples. So Pythagorean triples are just a group of three integers. They have to be integers, can't be decimals. Three integers that satisfy the Pythagorean theorem. Here's an example. You have 3, 4, 5. And I ordered these by A, B, and C. Right? You can see longest side is 5, and two shortest sides are 3 and 4. And if you substitute this into the equation, you get 3 squared plus 4 squared is equal to 5 squared. And if you do the math, that should work. Any questions about this? No questions? Okay, let's move on. Okay, so this is a link that takes you to an example of a proof of a Pythagorean theorem. There are multiple proofs, but I chose one that's pretty simple for you guys to understand. And the reason why I'm showing this is that it's really important in geometry to understand where your formulas are coming from before you use them. It's really good to know. So let's go to this link. Probably been to this website before. Math is fun, but they do a good explanation of the proof for a Pythagorean theorem. So here to explain what it is, and they prove it using algebra and then this diagram right here. So they have this large square and then another square inside that square. So here they're going to show that a squared plus b squared equals c squared without knowledge of the Pythagorean theorem like before. They're going to prove it right here. So what you do first is that you have to find the area of the entire square. And the area of a square is just you square the side length of the square just to get this area. So each side length is a plus b. So a plus b will give you a side length of the square, the side length of the square. And so total area is that you just multiply it by itself. So area equals a plus b times a plus b, or a plus b squared. And now you have to consider the area of the individual pieces. So here you have 4 right triangles, and then you have the smaller yellow triangle in here. So you're just going to count the area of those shapes. So first they found the area of the smaller square, which is just c squared. So c is the sine length of that smaller square. So you just square it to get the area. And then each of these 4 triangles, so 1, 2, 3, 4, these are right triangles, where you have the base equal to a and the height equal to b. Or you can also change them for base is b and height is a. And so each of those triangles have area of a times b divided by 2. Right? And since there's 4 of them, you just multiply that value by 4 to get the total area of the 4 triangles. So you have 4ab, 4 times ab divided by 2. That'll give you 2ab. And so now if you add up the area of the 4 triangles with the area of the small yellow square, you would get the area is equal to c squared. So from here, c squared plus 2ab from the triangles. And since those individual shapes add up to the area, so the area of those individual shapes add up to the area of the larger square, that means that they have to be equal. So you can equate the a plus b times a plus b with the c squared plus 2ab. And then you're trying to rearrange this just to get a squared plus b squared equals c squared at the end. And it's possible to do that. So you start with that equation, and then they expanded a plus b times a plus b, or a plus b squared. It'll look like this. So a squared plus 2ab plus b squared equal to c squared plus 2ab. And then they subtracted 2ab from both sides. So this is gone. This is also gone. Oops. So it's 2ab is gone. This 2ab is also gone. And you're left with a squared plus b squared is equal to c squared. And that's the proof of the Pythagorean theorem. Any questions about this? Oh, let the principal in. Okay, any questions about this proof? Oh, hello, Bob. Yeah, you 2 E10s. Okay. Nope. And Patrick's here, full class. All right, so for Bob and Patrick, we're learning about So here's what we learned. We're just going over, today's our topic is triangle geometry. We just went over like review of triangles and these terms that you need to know. Just take a brief look. And then we just went over the Pythagorean theorem, which also be reviewed to you guys. And we also just went over a proof on here. You can, I'll share the slide. Well, the slideshow is on Google Classroom, so you can take a look at the slides as you move on. So if there's no questions, I'm going to go to the next slide. So we're going to learn a new theorem. Some of you might know this, but it's called the triangle inequality theorem. So this theorem is used to determine if you can construct a triangle if you're given three side lengths. So this theorem states that the sum of the two shortest sides of the triangle must be larger than the length of the largest side. And so what this means mathematically, it means that say you have two short sides A and B, and say your longest side is C, you have to have A plus B larger than C. And here are some examples of the triangle inequality theorem in play. So for this triangle, you have three side lengths of 7, 13, and 18. A and B would be 7 and 13, and C here would be 18. So then 7 plus 13 would give you 20, and 20 is larger than 18. So that means you can form a triangle with these side lengths. Now for this triangle, well, it's not a triangle, but like you look at the side lengths, so you have 4 and 5, that's A and B. So 4 plus 5 would give you 9, and 9 is not larger than 10. So that means that this triangle, sorry, like these side lengths will not form a triangle. As you can see here, like no matter how you rotate the 4 and 5, they will not touch each other so that you form a triangle. Any questions about this? Any questions about this here? Yeah. Remember A and B are the shortest sides, the two shortest sides. C has to be the longest side of the triangle. That's how it's defined. Yeah. Welcome. Any other questions? Right. I think the next slide is just a problem. It's fairly simple. So here. So I have two 30-centimeter rulers and a single 1 meter ruler stick. Can I form a triangle using these three rulers? So just say yes or no if you know the answer. And tell me why as well. All right, why not, Jerry? Yeah. Yeah, perfect. So like say if I were to draw this out, say that was 1 meter. And 30 centimeters will like only reach over here. I'm just estimating. But they can't reach each other because these guys add up to 60. While this one is just 100. And obviously 60 is smaller than 100 centimeters. So that means you cannot form a triangle with these side lengths. All right, it's good. It's a fairly simple problem. Let's move on. All right. We're going to review parallel lines. So maybe some of you don't know this, but parallel lines, what they are is they just represent two or more lines that never intersect each other. And these parallel lines, they usually have interesting properties when you cross a line. So it's called a transversal, when you pass a line in between the two parallel lines. And these have to represent the angles. So here, say let's look at the first diagram. So this is called corresponding angles. And so here you have the two parallel lines, and these parallel lines are represented with these arrows right here. So that means they are parallel. You have the arrow symbol. And then with corresponding angles, you have so this is a transversal line. So this line right here is crossing these two parallel lines. And what this corresponding angles mean is that these angles right here, so you have one above here and then one above the second parallel, one above the first parallel line, and it's in between the transversal as well. And you have this angle above the second parallel line, and it's also in between the transversal. These two angles are equal to each other. So those are corresponding angles. And a better way you can memorize this is that you can form an F shape. Like this is an upside down F, but you can also do like this F right here. And whatever angles are inside that F, that means they're equal to each other. So that's one way you can memorize it. Here you have alternate interior angles. So what that means is that, so you have this angle right here, and you have this angle 1 and 2. Those are equal to each other, and they're on opposites. Notice that they're on opposite sides of the transversal. They're equal to each other. Same thing for angles 3 and 4. These guys are equal to each other. So this is one version of alternate angles. So it's the interior version. You can also have an exterior version. We won't focus on this too much. So we have alternate exterior angles. So you have angle 1 here equal to angle 2 here. And then you also have angle 3 equal to angle 4 here. This one's not as important as alternate interior. So you know. And finally, you also have co-interior angles. So you have this orange line is like a C. That's one way you can memorize it. So what this means is that this angle, the angle formed in between the C, the angles right here, they add up to 108 degrees. So this angle, you add them together, you get 108 degrees. Any questions about these? So this should be mostly review for you guys, parallel lines. All right, let's move on. Gonna look at congruent triangles. Whoops. Congruent triangles. Remember, congruent just means that they're equal in size and shape. That's what congruent means. So there are some methods that you can use to prove that two triangles are congruent. Usually, you'd think that we have to compare like all of the side lengths and all of the angles just to really make sure that there are two or more triangles are congruent to each other. But we only have to compare specific side lengths and angles. So we don't have to compare all of them, just a few of them. So here are the following properties that we can use. And here's a side note. So you can see the SSS, SAS, and you're like wondering what those letters mean. So S just represents side, A just represents angle. So it means SSS would represent side, side, side. So over here, you're just comparing if this is fairly straightforward. You're just comparing all the side lengths and see if they're equal. And if they're equal, that means that these triangles are congruent. Here are some different methods. So this one's called SAS, so side, angle, side. And notice that the A is between the two S's. So there's an angle in between the two sides that you're comparing. So you're comparing two sides and an angle of each other. And when comparing the angle has to be between those two sides. That's why it's called SAS. So this one's used pretty often, actually. Here's one called ASA, so angle, side, angle. So here's instead of instead of an angle between two side lengths, you have a side length between two angles. So you have angle, side, angle. And when you compare those, and if they equal to each other, that means the two triangles are congruent. So that's angle, side, angle. And finally, you have angle, angle, side. This one's not used very often, actually, but it's also good to know. So here you have an angle, and then a side. So the side length, unlike angle, side, angle, this side length is not in between the two angles right here. It's either on this side or on this side. So that's angle side. Any questions about these? Oh yeah, and also this symbol right here, it just represents congruence. So you have an equal sign and then with a curly line on top of it. That just represents that two triangles are congruent. Any questions about this? No questions? Check the chat. Okay. All right, good. Let's move on. Let's look at a problem with congruent triangles. So let ABCD below be a parallelogram where you have angle ABC equal to angle ADC. And you also have the side lengths AB equal to DC. And you also have side length BC is equal to side length AD. So notice that they have these tick marks just to represent that these side lengths are congruent. So the ones with one tick marks, they're equal. And then the ones with two tick marks, they're equal to each other, but they're not equal to the one tick marks necessarily. So then a diagonal is drawn from, or line is just drawn from vertice A to vertice C. All right, so there's a diagonal that's drawn, and then the problem states that you have to prove that triangle ABC is congruent to triangle ADC. ADC right here. So you have to prove that these two triangles are congruent. And you can use any of the four methods that I showed in the previous slide. Give you guys a minute to think about it. Actually, it should be a fairly simple problem. I'm going to take it up on the canvas. So parallelogram. You have a diagonal right here. What do they look like? So ABCD. CD. So oh, wait. Okay. Think my wait. Can you guys hear me? Yeah. Can you guys hear me? Okay, good. Okay. I think my my headset cut off just a little tiny bit. Okay. So here's the diagram. We also have these two side lengths are equal. And we also have these angles are equal. So this one, angle B or ABC is equal to angle ADC. Right? Does anyone know what method we should use to prove that these two are congruent? Yeah. So here we have one side. So we have AD is equal to BC. So AD is part of triangle ADC. BC is part of triangle ABC. And we also have side length AB. Here, I'll write these down. Sorry. So we have AD equal to BC. And we also have AB equal to CD. That was defined. So these two were defined in the question. Equals CD. And what about the third side length? You notice that the third side length is just a diagonal, and both the triangles share that diagonal. So I just write both triangles have side length AC. So it means obviously the side length of these two triangles are equal to each other. So, whoops, I would say both have AC. So they both share the side length AC. And so here you're just using side, side, side. So proving that all three side lengths are equal to each other. And that's how you prove that triangle ABC is congruent to triangle ADC. And there are some other methods you can use as well. It's like say you have these two side lengths, and then you also have the angle in between. So you can use side angle side as well. So you have AD is equal to BC, you have AB is equal to CD, and then you also have angle ADC is equal to angle ABC. So this angle equal to this angle. Using side angle side, you can prove that these two triangles are congruent. Okay, any questions about this problem? No questions? Okay, let's move on. Let's go on to the next topic. Similar triangles. So what does similar triangles mean? So we're not talking about congruent triangles anymore. We're talking about similar triangles. So these are just triangles that have matching angles that are congruent to each other. Congruent as an equal in value. And this doesn't mean that the triangles are congruent to each other, as the side lengths can differ. So here's an example. Say you have an equilateral triangle with side length of 1, so all three side lengths are equal to 1. And say you have another equilateral triangle with side length of 2. So they're obviously not congruent to each other because the side lengths are different, but they're similar to each other because their angles match with each other. Because like all equilateral triangles, they have 60, 60, 60 degree angles. So that means all equilateral triangles are similar to each other, actually. It's good to note. But what we can do to prove that triangles are similar, we don't necessarily have to match these angles with each other. We can compare the ratios of their corresponding side lengths to determine if two or more triangles are similar. And I'll show you example in the next problem. But you have this also the symbol for two similar triangles. It's just a curvy line like that. So you can put like triangle ABC is similar with this dash. Triangle ABC is similar to triangle blah blah blah. Any questions about this? Here, I'll show an example of the third point on this. So say I'll use that example of the equilateral triangles. Whoops. So this is a 1, 1, 1. So obviously the angles match with each other, but what I mean by the side length ratios, so that I have to match side lengths with each other. So this one would match with this side length would match with this side length, this side length would match with this side length. And what I mean by ratios is that you just divide one side length by the other. I should name these triangles, actually. I'll remove these. Call this ABC. C, call it D, E, F. And so that means AC would correspond to DF. Well, even though it doesn't really matter which one corresponds to which. But in this case, let's just use the current orientation of the triangles. So AC would match with DF, BC would match with EF, and AB right here would match with DE. All right, so what I mean by the ratios is you take DF, divide by its corresponding side, which is AC. And then the other ratios are EF divided by BC. And then the last one is DE divided by AB. There you go. So this is what I mean by the side length ratios. And so in a similar triangle, these would be equal to each other. I know I'm trying these equal signs, but it's weird. But okay. But I'm just showing you that DF divided by AC is equal to DE divided by AB is equal to EF divided by BC. And if you actually calculate that, it's just 2 divided by 1 for all of them. And that's equal to 2, right? So then this is what I mean by corresponding side length ratios. Any questions about this? Hopefully that wasn't a very confusing topic. Let's go on to a sample problem with similar triangles. Oh, sorry. Here's an example first. just go for another example, I guess, just to make it more clear to you guys. So if these two triangles are similar, that means I'm using these side length ratios. We have PR that corresponds to DF. So PR divided by DF is equal to PQ divided by DE right here. So PQ corresponds to DE, which is equal to QR divided by EF. So QR corresponds to EF. And notice that these ratios are all equal to 1/2. That shows that these two triangles are similar to each other. And if you know that these two triangles are similar to each other, that means you have angle P. I should have said QPR, but I decided to just use one letter angles for now. So angle P over here is equal to angle D. And angle Q would correspond to angle E, and then angle R would correspond to angle F. Those are equal. And then this is just like a therefore statement. If you've seen like mathematical like proofs and stuff, they always have like this therefore statement at the end just to like end their solution. That means like therefore triangle PQR is similar to triangle DEF, just like that, right? Any questions about this example? Hopefully that made the similar triangles thing a bit more clear to you guys, the concept. Right. If there are no questions, let's go on to a problem then. Right. So in the diagram below, find the value of S. So this sine length right here. I'll give you guys a minute to think about it. Oops, sorry. Wait. Right, find value of S. I think a minute passed, so let's take this up. Well, does anyone have an answer so far though? Just curious. Yep, 3 seems correct. So let's see why it's 3. Let's go into a new template. So, yeah, let me redraw diagrams. So this was 6, this was 9. This angle right here was 35 and 28 on the other side. 35 degrees, this one's 28 degrees. And you have another triangle, so that's the one with the side length S. So this S, this is 2. This is also 35. This is also 28. Alright, so I told you guys that this is a similar triangle problem, but we still have to prove that these two triangles are similar before we try to solve for S. And so we can just use the angles just to prove that they're similar. So we have corresponding angles, 35 and 35, and we also have the 28s that correspond to each other. And usually that already like makes the proof that these two triangles are similar, because that means that, so if these two are similar, these two are also similar, then the third one also has to be similar. And you can probably see why. So if you try to calculate for the third one, so you have 180 subtract 35 plus 28. Does anyone know what this is equal to? So 100, just so the third angle that we haven't calculated. What's the value of that? Does anyone know? So it's this right here. So what is this 180 subtract 35 plus 28? Now we have to calculate 35 plus 28 first. What is this equal to? 117 is correct. So this means that this is 117, and this is also 117. Right. So I'm just showing you that like you can just prove that there are two pairs of matching angles just to prove that two triangles are similar, because that obviously means that the third pair, so like the other like the unknown angles are also equal to each other. So yeah, it's a good thing to note. And now that we proved that these two triangles are similar, now we can use our side length ratios just to solve for S. So it's a little bit messy. Let me remove some stuff. So those are both 117. Now to find which sides correspond to each other. So here we would have 9. So the sine length of 9 correspond to the sine length of S. Here we would have sine length of 6 correspond to the sine length of 2 right here. So it's a little bit messy. This corresponds to that. This corresponds to that. All right. And so if we use our side length ratios, we can write we can divide this by this. So S divided by 9. So it looks like a 5, but it's an S, so bear that in mind. So S divided by 9 would be equal to 2 divided by 6. And as always, you can always like flip these around. So you can flip this S and the 9 around. You can have 9 divided by S, but then that also mean that you have to flip around this as well. So 6 divided by 2. So I mean, like whatever triangle you use for the numerator, what what triangle you got the numerators from, they have to correspond. So like S and the 2, they both come from this triangle right here. It means 9 and 6 have to come from this triangle right here. You can't say S divided by 9 equal to 6 over 2. Can't just flip around the numerators and denominators. So if we solve for S, we just get 2 over 6. We can simplify it to 1/3. And we multiply both sides by 9. Just get rid of the 9 in the denominator right here. And if you solve for that, you get S is equal to 3. All right, so it's value of S. Any questions about this? No questions? Check the chats. No. Just saw a bunch of threes. Okay, let's move on. I think there's just 3 problems at the end of the slideshow. There's 3 problems. Here's the first one. Here, given the three sets, so here's the first set, you have 2 comma 3. The second set is 3 comma 4. And the third set just has the element 5 and nothing else. So here are the 3 sets. Given these 3 sets, I choose a random number from each of these sets. So I can say I choose 2 from the first set, I can choose 4 from the second set, and the third set, I'm only limited to 5, so I have to choose that. So I choose a random number from each set to form the side lengths of a triangle. Now, how many combinations of side lengths are there such that the side lengths actually form a triangle? And then how many combinations are there such that the side lengths form a right triangle? So I'll give you guys a minute to think about this, how you approach it. So we'd have to use the concepts that we learned earlier. So the Pythagorean theorem, and then the triangle inequality theorem. So keep that in mind. Wait a couple more seconds. All right, let's take this up. So we have 2, 3 on the first set. We also have 3 comma 4. And then we have 5 in the last set. And the way I'd like to approach this is that I actually want to find like all the possible combinations we can do. And then from there we can pick which one to satisfy, these properties so that they form a triangle and then they form a right triangle. So can someone name me just one combination, just any combination from these 3 sets? I always put them in a tuple like this. Yep, so we can have 3, 4, and 5. What's another one? Just pretend we're not considering like the properties. I just want like all the possible combinations we can have. We have 2, 3, 5. All right, there should be 2 more. What's another one? 3, 3, 5. Yep. So 3, 3, 5. And last one. What's the last one? What have we missed? Right down here. 2, 4, 5. Perfect. Yeah, that should be it. All right. So someone tell me which ones of which of these like groups actually form a triangle. I'll just put a check mark on which ones that work. So someone tell me which ones. Yep, 3, 3, 5 works. Sorry, 3, 3, 5 works because 3 plus 3 gives you 6. That's larger than 5. So that works. What else works? Yep, this also works. So you have 2 plus 4. It's also 6. All right, and what else works? Yeah, 3, 4, 5 also works. 3 plus 4 gives you 7. And 7 is obviously bigger than 5. So we see that the triangle inequality theorem satisfies, since it's triangle inequality theorem satisfies all three of these groups, that means they can form a triangle. And then the last one right here, 2, 3, 5. So notice that 2 plus 3 is equal to 5, not greater than 5. So it has to be greater than 5, not it can't be equal to that large side length in order for the triangle theorem to work, right? Otherwise, you'd have this. So say you have sine length of 5, and you have to connect 2 and 3, and if that they're connected to 5, you have 2 right here. So same drawing a line right here. So that's 2, and I have another one right here, right here. So this is 3. So you can see that this does not form a triangle because like 2 and 3, they're forming a straight line with each other. And you can see you can't really see any angles or anything. So I mean this is not a triangle. This can't work, right? So the sum has to be larger than the side length. It can't be equal to it. Now, which ones form a right triangle? Someone tell me. I think there's only one. Yeah, there's only one. So remember the Pythagorean theorem, a squared plus b squared equals c squared. So a group has to satisfy that. Which one of these satisfies the Pythagorean theorem? No, it's 3, 4, 5. Yeah. So if we look at it, so we have 3 squared right down here, plus 4 squared. I'll calculate this. So this should be equal to 5 squared, but let's prove it. So 3 squared is 9, 4 squared is 16, 9 plus 16 gives you 25. And 25 is 5 squared. Right? So if I switch any of these numbers, so I say switch a 3 to 2 over here, or I switch the 4 to 3 over here, then this equality would not work. The Pythagorean theorem would not work. It would only work on 3, 4, 5. So that's the question. Any problems? Sorry, any questions about this problem? So I guess there's 3 combinations for the first part, and then there's only 1 combination for the last part. Any questions? Right. I'm not sure if we have time for the last 2. Like, I think we only have time for 1 problem, but let's see. We have 7 minutes left. Let's try this one out. So here, Kevin is standing vertically 3 meters away from a 10-meter tall streetlight. So streetlight right here, I named it AB, 10 meters tall. Here's Kevin. He's standing perpendicular to the ground, and he's 3 meters away from it. So I call this distance AC. So he's standing from a 10-meter tall streetlight, which is shining directly over his head. So say the light is at B, and B is shining directly over his head, so that it's touching it. It's like tangent to it, but like it doesn't cross through it. Say that light goes all the way over here. And so if Kevin is 2 meters tall, I know that's not exact height, but like I'm just making these numbers up just to make calculations simpler. Say Kevin is 2 meters tall. What's the length of his shadow on the ground? So it means the length from C over here to where B meets from where the light meets the ground. So from C to this point. That's the length of his shadow. Give you guys a minute to think about it. Think about how we approach this. And here's where parallel lines come in handy. Give you guys that hint. let's take this up. It's a bit of a challenging problem for you guys. Or maybe not, we'll see. Okay, so let's draw this diagram. We're going to just represent Kevin as a line now instead of a stick figure. So it'll look like this. So this distance is 3 meters. I'm just going to ignore the unit for now. This distance is 10 meters. And Kevin's 2 meters tall, so this distance right here is 2. Right? And then both the street light and Kevin, they're perpendicular to the ground, so these are right angles. And that means that they're also parallel to each other. Just like that. I use these arrows to represent that these two are parallel. All right. Does anyone know how we should approach this problem? Just curious. Like which concepts should we use from the lesson today? Yeah, side ratios or similar triangles. But the thing is, we first have to prove that these two triangles. So we have to prove that two triangles are similar to each other. So which triangles do we have? So I'm going to name these vertices just to make it simpler. So it is A. Oh yeah, the street light was called A, B. Forgot about that. This was B. A. And wherever Kevin was standing, we'll call that part C, as it will state in the diagram. We'll say wherever the light touches Kevin's head, that's D. And when the light touches the ground, we'll call that point E. So the only two triangles we have are ABE and we also have triangle CDE. So these are the only two triangles that we have in this diagram. And we're going to try to prove that these two triangles are similar to each other. And so we have to use some of those parallel line properties that we looked at a couple slides ago. So here, so we have to use any of these properties to prove that the angles are equal to each other, which means that the triangles are similar. So we know that these both of these are right angle triangles. They both have the right angle. So this one has it at A, this one has it at C. So we'll draw that out. Angle A. Well, okay, BAE. I'll just put it angle A. Angle A is equal to angle C because they're both right angles. What we also notice, actually just realized, yeah, we didn't have to use parallel lines. Sorry? Okay. I realized we probably didn't have to use these parallel lines. But I guess these are considered corresponding angles. So we have angle A and angle C. They're considered corresponding angles, like with the parallel lines right here. So angle A and angle C would be considered corresponding angles. So what we notice is that these triangles, they share this angle E right here. So they both have angle E. Both have angle E. Oh, skipping that word. And then in the other angles, so they have angle ABE, and we have angle CDE right here. So since we proved that angle A is equal to angle C, and then they both share angle E, so it means that angle is equal. That means that angle B has to equal angle D. You can also prove it by parallel lines, where these two are corresponding angles, but that didn't matter. So now that we know that those angles match each other, this means that triangle ABE is similar to triangle CDE. And now what we're trying to find is the value of CE. So this length right here. That's the length of Kevin's shadow. So we're trying to get. And so we can just do this with side ratios. So we can do CE. So CE would correspond to AC, and then we have DC would correspond to BA. So now we can use our side